start recording these sessions. Okay. And I will share my slide. Yeah. Okay, can you see my screen? Can you hear my voice?
Yes.
Okay, thank you. Thank you for the response. Okay, so last week we have learned about power in angle modulation. Okay, power in angle modulated signal, which is determined based on the Bessel's equations actually. Yeah. So previously we have learned about the power in angle modulated signal. So actually this is for both FM and also for PM. Okay, so this is true for both FM and PM. So the way we calculate the total power is equal to 1 over 2 Vc square multiplied with summation of Jn square from minus infinity to infinity. Okay, so this is actually the quadratic summations of relative amplitudes. Okay, again, if as we have learned last week that the relative amplitudes don't have any unit, it's a unitless parameter. If you remember that Jn is equal to Vn over Vc. Okay, it is a relative amplitudes which shows the ratio of real amplitude versus over carrier amplitude. Okay, so we have this Jn square from minus infinity to infinity. Okay, summation of Jn square summation of Jn quadratic from minus infinity to infinity. So again, as we have learned last week, that the power equations that we have learned in the previous years, we know that power is equal to V square over 2R. Okay, and if you see from here, there's a missing parameters, which is the resistance. Okay, so actually there's a resistance, there's a R parameters over here. Okay, where in this slide, in this example, we assume that the resistance is equal to unity, which is equal to 1. Okay, so don't be confused that actually there's resistance parameter in these equations. Okay, and actually there's R over here. Okay, so in this case, since R is equal to 1, so that's why it is not put the R in this example. Okay, so if you see from here, from this total power, we can say that the total power is finally becomes Vc square over 2R, which is actually equivalent to power of the carrier. Okay, so why it is like that? Okay, why it is like that? And as I mentioned last week, that this parameter, this parameter, summation of Jn square from minus infinity to infinity. So this parameter would be equal to 1, okay, because according to the Bessel properties, okay, according to the Bessel properties, that summation of Jn square from minus infinity to infinity will produce a value equal to 1. Okay, so this is according to the Bessel. Okay, so since this becomes 1, therefore the total power of the angle modulated signal will become equal to the carrier power. And if you see that the total power is actually equal to this unmodulated carrier power, Vc square over 2R. Okay, so if you ask me, can I uh, do total power equal to Pc? Okay, can you do like this, Pt equal to Pc? Okay, so the answer is yes, you can do like that. Okay, because the total power in angle modulated signal is equal to the carrier power. Okay, so um, in the exam, if you do like this, it is correct. Okay, it is correct. But you should also see the total marks given in the question. Okay, so if the marks is around 2 marks, which is very small, so you can do like this. But if the marks for that question is more than 2, I suggest you to use the long equations, which is this one. Okay, so this is the complete equations for total power in angle modulated wave, which is equal to P0 plus 2 times P1 plus P2 plus P3 until Pn. Okay, so why do we multiply it with 2? Because we have upper sideband and also the lower sideband. Okay, we have the upper sideband and we have the lower sideband. So that's why we need to multiply with 2. Okay, to accommodate both lower and the upper sideband. Okay, so basically as we have learned in AM previously that the total power when we want to calculate the total power we added we adding all the power component for each of the spectrum. Okay, similar with this one also, we added all the power component in the spectrum so that we can get the total power. Okay, and if you see from here that uh, P total is equal to V0 square over 2R plus 2 times V1 square over 2R, V2 square to R, V3 square to R until Vn square over 2R. Okay, where Vn is actually equal to Jn multiplied with Vc. Okay, so from here, you see that uh, from here you see that this is actually for example here, so this is actually J0 multiplied with Vc, okay, square. This is J1 Vc square. This is J2 Vc square. This is J3 Vc square. And this is Jn Vc square. Okay, so you see that um, in each component we have Vc square over to R. Okay, we have a Vc square over to R, Vc square over to R, we have Vc square over to R, and so on. So in each of the component we have the Pc. Okay, which is why we put like this, J0 square Pc. Okay, because we have a Pc over here, Pc, okay, Pc, and so on. So that's why we can rearrange the equation to become J0 square Pc plus 2 times J1 square Pc plus J2 square Pc plus J3 square Pc plus until Jn square Pc. And for your information, theoretically, all of this would become equal to Pc. Okay, theoretically. But if you use the um, Bessel table in your notes, you might found that it is approximately equal to Pc. The difference is just about 0.0 something values. Only a few decimal point difference. Okay, for example, you get theoretically you get 10 watt. Okay, so when you use your Bessel table in your notes, you might get 10.02 watt, something like this. Very small. The difference is very small. So that's why if you use the Bessel table in your lecture, in your notes, you might get approximately equal to PC. The difference just in terms of a few decimal points. Okay, so if you get the difference might not up to 1, just a few 0 point something, very small. Okay, so you will see later in the example. Okay, you will see later in the example. And for your information, in the final exam later, there might be a question about the total power. Okay, there might be a question about the total power where the marks given would be 6 marks. Okay, and you might need to use the long equation to calculate the total power. And you might need also, the question also asks you to compare with the unmodulated carrier power, which is PC. So you might need to show the difference, how many difference between the unmodulated carrier power and the total power produced with the long equations. Okay, so that's about the final exam later. And let's look for the example. Okay, so about this issue, you might see later in the next example. Okay, so we will go through the first example, 3.7. An FM signal is given as 12 VFM of t equal to 12 cos 6 pi times 10 power of 60 plus 5 sine 2 pi times 12 1250 t volt. Okay, so from these equations, from this question, I would suggest you to extract all the given information. Okay, for example, from this equation, I know that this is actually equal to VC. And from here, I know that this is actually what? So this is actually 2 pi times 2 pi FCT. Okay, so this is actually equal to 3, sorry. So this is a FC. So FC is actually equal to 3 times 10 power of 6. Okay, hertz. You need to divide with 2 pi. Okay, bahagikan dengan 2 pi. If you divide with 2 pi, you're going to get 3 multiplied with 10 power of 6. So this is actually 3 mega. Okay, 3 megahertz. Plus 5 sine. So what is this actually? As we have learned previously that this is actually referring to the beta parameter, the modulation index. Okay, beta equal to 5. Okay, and sine of 2 pi multiplied with 1250. So what is this? This is actually the modulating signal frequency, the input signal frequency, which is 1250 hertz. Okay, so now what? Now the question asks, determine the frequency of the carrier. Oh, I already know that from the question, the frequency of the carrier is equal to 3 megahertz. Okay, so this is actually 3 megahertz. Okay, 3 megahertz. And then what? Frequency of the modulating signal, which is FM. Okay, so this is FC, this is FM. Frequency of message, frequency of modulating signal, which is equal to 1250 hertz. Okay, 1250 hertz. And then what? Modulation index. Modulation index beta f is equal to 5. Okay. And then what? Frequency deviation. Okay, frequency deviation is actually equal to delta f. Okay, so this is actually equal to delta f. So delta f is actually equal to beta f Vm. Okay, so if you remember that beta f, so beta f, as we have learned previously, that beta f is actually equal to delta f multiply divide with fm. Okay, so if you want to find delta F, that means delta F is equal to beta F multiplied with the modulating signal frequency. So you will get this 5 times 1250. Okay, 1250. So you will get how much of this? So 1250 multiplied with 5. So 6250. So you can do like this, 6.25 kilohertz. Okay, 6.25 kilohertz, so 25 kilohertz. So could you please also to check my answer? If my answer is wrong, please correct me. Okay, so 5 times 1250, you will get 6.25 kilohertz. Okay, and then what? The last question is to find the power dissipated in 10 ohms resistor. Okay, find the total power dissipated in 10 ohm resistor. So this is about the total power PT. Okay, so again, this question does not specifically ask you to use a short equation or long equation. So in this case, assuming that the marks given for this question is, for example, only 2 marks, for example, okay, then I will use the short equation, which is P total equal to PC. Okay, so this is equal to VC square divide with 2R. So you can get this as a 12 square, okay, 12 volt square, divide with 2 times the resistance, which is 10 ohm. Okay, so this how much? 12 square divide with 20, so you get 7.2. 7.2 watt. 7.2 watt. Okay, so 7.2 watt for the total power. Okay, if you want to use the long equations, that means you need to know how much is the voltage for each of the spectrum. So you see that this is the modulation index is equal to 5. So if you want to use the long equation, that means you need to refer to the Bessel table. Okay, refer to the Bessel table for modulation index equal to 5. So I go back to the Bessel table. So I go back to the Bessel table. So modulation index equal to 5. You will get up to 8 pairs of sideband. So that means n is equal to 8. Okay, so n is equal to 8. So you have a J0. Okay, you have J0 until J8. Okay, and you need to find how much is V0. Okay, how much is V0 until V8. Okay, so once you know the values of voltage, the amplitude, then you can find the power, which is over here. You can use for example, P0. Okay, P0, how much is P0 until P8. Okay, and then you can find the total power. So P total is equal to P0 plus, okay, P0 plus 2 times P1 plus until P8. Okay, the 8th sideband. Okay, so you can get the final answer in term of watt. So this, if you want to use the long equation. Okay, and if you use a long equation, you can try yourself. You can try yourself. You will get the total power 7.2 something. Okay, very almost similar with 7.2. Okay, which which what we have calculate which is equal to PC. Okay, so you can try yourself. Okay, try yourself using the long equation, how much you get. So you get 7 point something, which is very close to the power of the carrier. Okay, so I go back to the slide, to the previous slide, which is this one. Okay, so if you use the long equation, you might get almost similar to the 7.2 watt. Okay, boleh cuba try. So if you have question about this, please ask me question. Okay, kalau ada soalan sila tanya. So if you don't have question, I will move to the next example. Okay, so no questions. So let's look at the next example. Okay, the next example. So the next example, 3.8, determine the unmodulated carrier power for the FM modulator given that beta is equal to 1. Okay, so beta is equal to 1. VC is equal to 10 volt, resistance at 50 ohm. Determine the total power in angle modulated wave. So you see that here, suddenly there's a statement about this. There's a statement at the end here. Not exactly equal because the values in Bessel table has been rounded off. So this example is actually wants to show you the difference of total power using the long equations and compare to the unmodulated carrier power. So from there we can see the difference. Okay, so let's do this example so that you can see what happened actually. Okay, so for beta equal to 1, okay, for beta equal to 1, you will get beta is equal to 1. That means the number of significant sideband n equal to 3. Okay, so from the Bessel table, you will get J0 equal to 0.77, J1 is equal to 0.44, J2 is equal to 0.11, J3 is equal to 0.02. Okay, so from here you can determine the value of voltage. Okay, the value of voltage. So let me check the Bessel table. So 774411 and 02. Okay, so this is correct from the Bessel table. So from here you can determine you can determine how much is V0 until V3. So V0 is equal to J0 multiplied with VC. So you will get this equal to 7.7 volt. This is V1 is equal to J1 multiplied with VC. So you get 4.4 volt. This is V2 is equal to J2 multiplied with VC. So this is 1.1 volt, and this is V3 equal to 0. J3 J3 multiplied with VC. So this is J3 multiplied with VC. So you will get this one 0.2 volt. Okay. So again, if you use P0, P0 is equal to V0 square over 2R. Okay, so you will get this how much? So let's calculate together so that we can find the correct answer. Okay, so this is 7.7 square divide 7.7 square divide with 100. So 0.5929. Okay, so please correct me if I'm wrong. So P1 is actually equal to V1 square divided with 2R. So this is how much? 4.4 square divided with 100. So we get 0 0.1936. 0 0.1936 watt. So P2 is equal to uh, V2 square divided with 2R. So this is 1.1 square divided with 100. So you get 0 0.0121 watt. And P3 is equal to V3 square divided with 2R. So this is 0.2 square. 0.2 square divided with 100. So you get uh, 4 times 10 power of minus 4 watt. Okay, so if you plus all of this, okay, if you plus all of this, P total is equal to P0 plus 2 times P1 plus P2 plus P3. Okay, so from here, see that this is 0.5929 plus 2 times 0.1936 plus 0.0121 plus 4 times 10 power of minus 4. Okay, and then close bracket. So let's calculate together. Okay, cuba calculate sama-sama plus 0.0121 plus 0.1936. Okay, so this is 0.525929 plus 2 times bracket 0.2061. So this is supposed to be times 2 plus 0.5929. So you will get 1.0051. Okay. So this is total power using the full equations. So what if you find the carrier power? So let's find the carrier power. So if you calculate the carrier power, okay, PC is equal to VC square over 2R. Okay, so if you see here, VC is equal to 10. Okay, so 10 volt square divide with 2 times 50 over here. So how much? 100 and 100. So you will get 1 watt. Okay, so theoretically you will get 1 watt. But when you use the Bessel table in your notes, you will get 1.0051. Okay, which is very close to the theoretical value. Okay, so that's why in this example it comes up with the statement below. It shows that the theoretical value is not exactly equal with the total power from the Bessel table that we use at the long equations, because the values in Bessel table has been rounded off. What do you mean by rounded off? Because if you see from your Bessel table in your notes, all values less than 0.01 neglected, uh, has been erased or has been omitted from the table. Okay, so that's why the value is slightly different. Okay, that's why the value is slightly different with the theoretical value. Okay, so do you have question about this? Kalau ada soalan, you are most welcome to ask question. And if there's no question, we can move to the next example, which is example 3.9. Okay, Okay, example 3.9. So this is a good example for the final exam. So if you ask me, your final exam question is almost like this, something like this. Okay, the question is structured like this. Okay, and it will ask you up to power calculation and so on. Okay, so let's go through the example 3.9. Okay, example 3.9. An FM signal expressed as VFMT, 1000 cos 2 pi 10 power of 7t plus 0.5 sine 2 pi 10 power of 4t is measured in a 50 ohm of antenna. Determine the following. Okay, so again, once you are given a question, straight away you need to extract the important parameters. Okay, so from the questions we know that this is referring to the carrier amplitude VC 1000 volt. Okay, and what is this? This is 2 pi times 10 power of 7. That means this is FC. So FC is actually equal to 1 times 10 power of 7 hertz. Okay, because this is actually 2 pi F. Okay, 2 pi F. And then what? And then we have another parameter which is 0.5. So this is actually the modulation index. And another parameter is 2 pi 10 power of 4, which means this is actually the modulating signal, which is 1 times 10 power of 4 hertz. Okay, or we can say that this is 10 kilohertz. Okay, and you are given R over here. R is 50 ohm in the antenna. So determine the following: unmodulated carrier power. Okay, the carrier power, so which is equal to PC. So PC is equal to VC square divide with 2R. Okay, so PC is equal to VC square divide with 2R equal to VC square divide with 2R. So this is actually 1000 square divide with 2 times 50. How much is this? So 1000 square divide with 100. So you will get 10,000. Okay, very big. 10,000. 10,000 of what? 10,000. Make sure you write the unit. 10,000 watt. Okay. If you don't write the unit, that means your answer is wrong. Okay, 10,000 and 10,000 watt are two different things. Okay, so be careful about that. Okay, so the next questions is modulation index. So modulation index based on the given question. So beta is equal to 0.5 straight away from the question. Okay, and then what? Frequency deviation. Frequency deviation is delta F. Okay, so delta F is actually equal to beta. You can write beta or beta F, doesn't matter. Okay, tidak ada masalah, beta or beta F. So for example, beta F multiplied with modulating signal frequency, so you will get delta F. So in this case, it is actually 0.5 multiplied with 10 kilohertz. Okay, 1 times 10 power of 4 is actually 10 kilo. Okay, so it is like this, 10. So 10 kilo. There are 4 zeros, so that means 10 kilo. Okay, so here you will get this is actually equal to 5 kilohertz, half of it. Okay, separuh saja. And then what? So class, if you have question, please ask. Otherwise, I will move to the next sub questions. Okay. So the next sub questions number 4 asks you to find the modulation sensitivity parameter if 200 millivolt is required to achieve part C. So part C here is actually part question number 3. Okay, question number 3. So you are given a determine modulation sensitivity parameter, which is KF. So you need to find the KF if you are given this parameter. Okay, what is this actually? So this voltage is needed to achieve delta F, this one. So this is actually referring to the peak amplitude of the input message. Okay, because this is the value to achieve the delta F. Why is it like that? Because delta F is actually equal to okay, delta F is actually equal to KF VM. Okay, KF. So now you need to find, okay, so you are given this one in the question, VM is given, and you need to find KF. Okay, so KF, okay, so this is 5. So 5 kilo divide with 200 milli. So I get, okay, so 25 kilohertz per volt. So this is for question number 4. Okay, question number 4. Then what? Then the question asks to find the amplitude spectrum. Okay, so if you want to find the amplitude spectrum, that means you need to refer to the Bessel table. Okay, you need to refer to the Bessel table. So if you read from the Bessel table, beta equal to 0.5. So you need to find what is the value for each of the V, the amplitude parameter. Okay, so from here, yeah, I will erase this one. So where should I write? So maybe I can so for beta equal to, yeah, beta. So I try to write here. Okay, so let's try to write here. So beta equal to 0.5. the value of number of significant sideband is equal to 2. Okay, number of significant sideband is equal to 2. That means you can find J0 is equal to 0.94. 0.94. J1 is equal to 0.24. J2 is equal to 0.03. Okay, so this is from the Bessel table. Okay, so in order to find the amplitude, okay, in order to find the amplitude, so the amplitude is first you need to find V0. V0 is equal to J0 multiplied with Vc. Okay, so here that means 0.94 multiplied with 1000, so you will get 940 volt. Okay, you multiply with 1000. 1000 is the Vc, so 940. V1 is equal to 240 volt, and V3 is equal to 30 volt. Okay, so once you know this, you can draw the frequencies, you can draw the amplitude spectrum. Okay, so remember amplitude spectrum, that means you need to draw amplitude versus frequency. Okay, which is V versus F. Okay, and here you have this the carrier. Okay, so this is 940. Okay, and you have the first, here is 240, and another one here is 30 volt. And you have also the lower sideband. Okay, the lower sideband over here, 240, and another one here is 30. Okay, and this is not complete yet. Okay, this is not complete yet. Remember that we also need to find the frequency. Okay, for example, here F is in term of megahertz. Okay, megahertz. So here is 10 mega for the carrier frequency. Okay, 1 times 10 power of 7 is actually equal to 10 mega. Okay, so the first sideband is 10 mega plus FM. Okay, 10 mega plus 10 kilohertz. So this is actually 10.01. Okay, and another one here is 10.02. Okay, so and then for the lower frequency is 10 10 mega divided with 10k, so you get 9.99. This is 9.99, and this is 9.98. Okay, so this is the amplitude spectrum. So when you do the amplitude spectrum, you need to label the axis, you need to label the amplitude, and label the frequency. Okay, so here the center is 10 mega, 10 mega at the center, and then you just need plus FM plus 2 FM. Okay, so this is actually FC plus FM, this is FC plus 2 FM. Similar with the other side is FC minus FM. Another one here is FC minus 2 FM. Okay, so you get the amplitude spectrum. Okay. If you don't understand, you can ask question about this. If no question, I will move to the next sub questions. Okay. So again, when you draw the amplitude spectrum, the frequency is Fc, Fc plus Fm, Fc plus 2 Fm, Fc plus 3 Fm, and so on. Similarly, with the lower sideband, Fc minus Fm, Fc minus 2 Fm, Fc minus 3 Fm, and so on. Okay. So question number 6. Okay. Bandwidth of 99% and the approximate bandwidth by Carson's. Okay, and the approximate bandwidth by Carson. So how to do this? So wait, so I need a bigger, yeah. Maybe I can go to the next slide. So let's try a new slide over here. Okay. So bandwidth by Carson 99%. So so now we need to find the bandwidth by Carson. Sorry, bandwidth by Bessel. Okay, bandwidth by Bessel. So bandwidth by Bessel, if you see from your lecture notes, is equal to 2 times n times Fm. Okay. So based on the Bessel table, it is actually 2 times how many n we have? N is equal to 2. Number of significant sideband for beta equal to 0.5, you get n equal to 2. Okay, so that's why multiplied with 2 multiplied with the modulating signal frequency is 10 kilohertz. Okay, so 10 kilohertz. So this is actually equal to 4, so 40 kilohertz. Okay, 40 kilohertz. But the question asks you about 99% of the bandwidth. Okay, 99% of the bandwidth. That means this is related to bandwidth by Bessel. 99% of 40k, so 0.99 multiplied with 40 kilohertz. So you will get how much of this? 0.99 times 40k. So you will get 39.6 kilohertz. Okay. And then what? The question also asks you to find the bandwidth by Carson. 99%. Okay. So bandwidth by Carson. So first of all, you need to find bandwidth by Carson, which is 2 times delta F plus Fm. So this is actually equal to 2 times. How much is delta F? We already find delta F is equal to 5. Okay, from question number 3. Okay, so question number 3, 5 kilo. So 5 kilohertz. Okay, 5 kilohertz plus 10 kilohertz given from the question. So 15 times 2, so we get 30 kilohertz. Okay, but the question asks you to find bandwidth Carson 99%. 99%, which is 0.99 multiplied with 30 kilohertz. Okay, so you will get this, how much? 0.99 times 30k. So 29 0.7 kilohertz. So this is bandwidth 99%. Okay, bandwidth 99%. So we get this answer for both Bessel and Carson. Okay, and then what? Then the question asks you, okay, so class, if you don't understand, please ask me question about this. Otherwise, I assume that you understand. Okay, so the next question, okay, this is from the previous 99. So you just need to multiply it with 99%. Okay, you just need to multiply with 99%. So the next question asks you find the smallest sideband of the 99%. Okay, so you see that maybe I can redraw again. Okay, so this is 940. Okay, so you see that this is 10, 10.1. 10 point, so 10. Okay, so this is in terms of megahertz. So if you see from here, can I use a different color? So if you see from here, the total bandwidth, okay, the total bandwidth, if we consider the full bandwidth by Bessel, it is actually, you see the distance is actually 40, 40, sorry. The distance is actually 40 kilohertz. Okay, 40 kilohertz. And if it is a 99%, that means it is somewhere, it is smaller than this. Okay, 99% is smaller than 100%, so that means it is somewhere over here. Okay, we can do something like a filtering process. So this is a 99%. So 99% you will get only 39, which is so this is 39.6 kilohertz. Okay, so if you have a band pass filter, you cut off a 99% like this. So that means um, the smallest sideband here will be removed. Okay, will be removed by the filter. Okay, so assume that we have a filter that will have a 99 cut off. So that means the filter will select everything inside here within this 39.6 kilohertz of bandwidth and remove the others frequency. So that means the smaller sideband here will be removed. Okay, if you have a band pass filter. Okay, kalau kita ada band pass filter, that means this band pass filter, if you use a band pass filter with a bandwidth of 39.6, so that means starting from the center, so 39.6, so that means we will cut off the smallest spectrum, the smallest component over here will be cut off. And if you see the question asks you power in the smallest sideband of the 99%. Okay, so in this case, it doesn't matter whether you want to use 99% of Bessel or 99% of Carson. Okay, so if it is a 99% of Carson, that means it becomes smaller over here. Okay. Again, the smaller sideband also will be cut off. Okay. So if you see from here, within the 99%, the smallest sideband would be this one. This is the smallest sideband. Okay, which is the first sideband, not the second. Okay, the first sideband would be the smallest sideband. So in this case, the question asks you to find the power in the smallest sideband. That means you need to find the power of P1, which is equal to V1 square divided with 2R. Okay, so this is actually equal to 240 square divide with 2 times R is equal to 50 ohm. Okay, so you will get, how much is this? So 240 for 240 square divide with 100, so you get 576. Okay, power in the smallest sideband. Okay, so if you ask me, we have asked this kind of question in the previous semester. Okay, where in the question there are additional filter is put into the transmitter after the modulator. So I'm not remember the question. The previously we have something like the modulator over here. Okay, the modulator, and then we have another filter over here, band pass filter. Okay, so if you see in that question previously, uh, so the modulator produced the FM signal where you need to find the total power, okay, using the Bessel equations, using the Bessel. Okay, this is 100% of total power. And then there's another bandpass filter over here which will limit the spectrum. Okay, and the question also asks to find the new total power, P total new. Okay, so the bandpass filter eliminate the unwanted frequency spectrum. So the remaining, you need to find the total power. So this example reminds me of the previous final exam questions. So we have asked this kind of question, I think once previously, regarding this difference of total power. So previously we have first we have the 100% total power, and then we have the bandpass filter which will limit the spectrum component. Then we need to find the new total power which is smaller than the previous total power, because the bandpass filter already removed the unwanted spectrum. Okay, so that's about that's about these questions and also the previous final exam. Okay, I just remember about the previous semesters of final exam questions. So I will erase this. And let's look the next question. So next question asks you to find the total power. Okay, find the total power, P total. Okay, so you see that uh, this total power is actually not related to the previous bandwidth 99%. Okay, so if this total power is based on the what they call after we put the bandpass filter, that means we only need to consider the carrier and also the first spectrum, upper and lower. Okay, the first sideband, upper and lower. But in this case, the total power is is actually related to the total spectrum. Okay, so that's why this question is what they call is not related to the previous. Unlike in the previous final exam, where we put the bandpass filter, so the total power is different from before we put the bandpass and after we put the bandpass filter. Okay, so now the total power is equal to how to do this? So if you ask me, total power, we can put total power is equal to unmodulated carrier power. Okay, which is equal to PC. So P total is equal to VC square divided with 2R. So in this case, it is uh, okay. So we already find the unmodulated carrier power. Okay. So we have already find the unmodulated carrier power. So the final answer would be almost 10,000 watt. But in this case, let's try to use a long equation. Okay, dalam case ini, let's try to use a long equation. Because we already know that the total power is actually this one, 10,000. We already calculated previously. But for this example, okay, for this example, let's try to use the long equations, okay, which is, sorry. So let's try to use the long equations. So P0 plus 2 times P1 plus P2. Okay, so this is actually equal to, so 940, this is how much? 940 and 940 square divided with 100. So you get 8836. So this is 8836. So 940 square divide with 100, so you get 8836 plus 2 times P1. P1 is 240 square divide with 100, so you get 576 plus P2 is 30 square divide with 100, so you get 9. So 576 plus 9 times 2 plus 8836. So you get 10,006. Okay, 006. So the difference are only 6 watt compared to 10,000. Okay, which is very small. So do you have question to ask about this? Ada soalan nak tanya? Okay, so no question. So we can go to the next example.
Yes, sir.
Wait. Check one, two, three, four, page. Okay, so uh, okay, so let's before we move to the next example, there's also eight, eight, two, five, seven, six. Okay, so about this total power. So what I did previously is that I didn't consider the previous the that means I didn't consider that we put a band pass filter. Okay, so if let's say the question is continuous, after band pass filter calculate the total power. That means your total power is only equal to P0 plus 2 times P1. Okay, so again, in my example, since the question is not stated clearly what is the total power means over here. So if it is total power of 99%, that means total power after we put the band pass filter. That means maybe I can put like this, P total of 99%. Okay, where within this 99% of the coverage of the bandwidth, so that means I only get P0 plus 2 times P1. Okay, 2 times P1. So this is total power within this 99% of uh, bandwidth. But if we consider the total power all, that means we need to consider all the frequency component within that frequency band. Okay, which I have done this 10,006. Okay, so this is if we consider 99%. And uh, there's also another parameter that uh, can be asked, which is total information power. Okay, total information power. So if I can, so let me erase some of this. Another parameter that can be asked is total information power. Okay, so total information power, which is equal to 2 times P1 plus P2. So why it is like that? Because information only contains within the sideband, where the carrier does not carry any information. So this is similar concept with the AM. Okay, so sidebands carries the information. Carrier does not carry any information at all. So that means 2 times, okay, 576 plus 9. So this is equal to 1170 watt. Okay, so this is if the question asks you total information power. So we need to calculate the total power in the sideband only, because the sideband carries the information. Okay, so total information power is actually the total power for the sidebands only. Okay, 1170. Okay, so let's go to the next example, example 3.110. Okay, so example 3.110, an FM signal with a 5 watt of carrier power is fluctuating at the rate of 10,000 times per second from 99.96 megahertz until 100.04 megahertz. Find what? Okay, so uh, so it is actually like this. So we have this. So the carrier fluctuates from 99.96. So this is actually F mega. Okay, so the carrier fluctuates 99.96 until 100.04. Okay, this is 100.04 megahertz. So it fluctuates, that means it's move it move okay, it moves from 99.96 until 100.04 for about 10,000 times per second. That means within one second it already fluctuates 10,000 times, 10,000 cycle per second. Okay, so what does it means? Okay, so this 10,000 is actually referring to the rate of information signal. Okay, so if you ask me, this is actually referring to the frequency of the modulating signal. Okay, so the carrier move from lower frequency, from fc minus delta f. So this is actually fc minus delta f until fc plus delta f. Okay, so the carrier move for about 2 delta f 2 delta f 2 delta f for about 10,000 times in 1 second. Okay, so this is what we call as the carrier swing, the total range of fluctuations from the lowest frequency to the highest frequency. Okay, so the question and then if you see from here, the lowest frequency is 99.96, the highest would be 100.04 megahertz, and therefore the center would be the rest frequency, which is fc. Okay, the center would be the rest frequency, which is fc. Okay, so let's go to the questions. So the first question asks, find the carrier frequency, which is fc. So fc is the rest frequency, which is located at the center of the fluctuations. Okay, so how to find that? That means so if you ask me 100.04 plus 99.96, okay, So this is FC. So FC is equal to 100. So this is 100.0499.96 plus 100.04 divide with 2. So you get this is 100 megahertz. Okay, or you can also do like this. You can also do like this. 99.96 megahertz plus 100.04 minus this is bracket 100, yeah, plus 100.04 minus 99.96 divide with 2, half of it. Okay, so you get 100. So starting from 99 plus 100.04 minus 99.96 over 2 divide with 2, so you get 100. So it is actually the center frequency. Okay, the center frequency. Okay, so this is the carrier. And then for the carrier swing, can I get your response? Are you still there? Can you hear my voice?
Yes,
Yes,
doctor.
doctor.
Okay,
Yes, doctor.
I'm worried I'm talking to myself. Okay, because you are too quiet. Okay, so the carrier frequency is the center frequency. Okay, so in this case, either you can use you plus the highest and the lowest and then divide with 2, or you can start from the lowest, 99.96, plus the difference divide with 2, or the carrier swing. This is a carrier swing divide with 2, so you get 100 megahertz, the center. Okay, so the next question asks about the carrier swing. The carrier swing, as I mentioned earlier, it is the range of frequencies from the lowest until the highest frequency. Okay, so that means, so this one is carrier swing is equal to the highest frequency 100.04 megahertz minus 99.96 megahertz. Okay, so how much is this? 40 and 40, so this is supposed to be 80 kilohertz. Okay, so please check using your calculator. So 40 kilohertz upper and 40 kilohertz lower frequencies. So total is 80 kilohertz. Okay, and then what? Carrier frequency deviation. So frequency deviation delta F is actually equal to carrier swing. So carrier swing divide with 2. So you get 80k divide with 2. So you get 40 kilohertz. Very simple. Okay, 40 kilohertz. And then what? Find the modulation index. Okay, so modulation index, as we have learned previously. Okay, so modulation index beta f is actually equal to delta f divide with fm. Okay, so delta f is 40 kilohertz divide with modulating frequency is the number of fluctuations per second, which is 10,000 times per second, or you can say that the frequency is 10,000 or 10 kilohertz. So 10 kilohertz means that the number of fluctuations is 10,000 times in 1 second. Okay, so therefore it is equal to 4. Okay, beta f is equal to 4. Okay, and then what? Then the question asks you to find the power spectrum. So power spectrum, that means we need to do a lot of things to do. There are a lot of things to do. So where should I write this one? So maybe I need another slide. Wait, so let's add another slide. One, two slide. Okay. Okay. So for beta equal to 4, how much is the number of significant sideband? Remember, when you want to do, so this is actually referring to the power spectrum. So the question actually asks you to draw the power spectrum. Power spectrum means that power versus F. Okay, power versus F. And in order to draw the power spectrum, you need to refer to the Bessel table. How many spectrum are there? Okay, how many spectrum are there? So if you see from the Bessel table, okay, from the Bessel table, so I will go back to the previous slide, this one. So n equal to beta equal to 4. So you will get up to 7 pairs of sideband. Okay, 7 pairs of sideband. That means n equal to 7. Okay, that means you're gonna have a 7 pairs of upper sideband and 7 pairs of lower sideband. Sorry, 7 upper sideband and 7 lower sideband. Okay, so 7 pairs, upper and lower. So I go back to the slide. So that means so when you want to do when you want to answer these kind of questions, okay, when you want to answer this kind of questions, you need to draw a table. Okay, you need to draw a table because we need to find the power and also we need to find the frequency as well. Okay, so so if you ask me, I would draw a table like this. Okay, so the table is actually so this is G square. Can we have PC or not? PC or PC? G square PC. Okay, so this is PC 10 times. So you already been given the carrier power 5 watt. Okay, carrier power is already been given 5 watt. So you can find the rest of the powers in the spectrum. So if you ask me, I would draw a table, and later in the final exam you also need to draw a table as well. Okay, so you can practice to draw the table. So the table is you can say that this is Jn, for example. Okay, so the Jn is, so this is the power, and then we have the LSB, lower sideband frequency, and the upper sideband USB. Okay, so if you see from the table, okay, if you see from the table, the first J, so J0 is equal to negative 0.4. Okay, so negative 0.4, that means the power P0 is actually equal to J0 square PC, which is equal to negative 0.4 square multiplied with 5 watt. Okay, so you will get this equal to 0.8 watt. Okay, so you can put here watt, you can put here in term of hertz, so you don't need to write the value each time. Okay, and so J0, sorry, P0 is located at the center, so it is not the sideband. Okay, it is not the sideband. And we move to the next value, which is J1 is equal to negative 0.0707, negative 0.07. That means P1 is equal to J1 square PC, okay, which is equal to uh, 0.07 square times 5. So you will get this equal to 0.0245. Okay, in terms of watt. What about the frequency? The frequency, it is located, it has a lower sideband and it has a upper sideband. So this is located at Fc minus Fm, which is equal to 100 megahertz minus Fm is 10 kilos. That means 0.01 megahertz. So you get the frequency is equal to 99.99 megahertz. So this is supposed to be megahertz. Okay, 99.99 megahertz. And here is Fc plus Fm. So it is supposed to be 100 plus 0.01. Why 0.01? Because our modulating signal frequency is 10 kilo. So that means this is 100.01 megahertz. Okay. And then J2. The second component is equal to 0.36. Okay. So you have here is P2 is equal to J2 square PC. So you get here is 0.36 multiplied with 5. This is square. So you get this equal to 0.648. Okay. And what about the frequency? The frequency is located at Fc minus 2Fm, which is equal to 100 mega minus, okay, 100 mega minus 2 times 10k, 0.01. So you get here is 99.98 megahertz. What about the upper frequency Fc plus 2Fm, which is equal to 100 plus 2 times 0.01, which is 2 times 10k. So you get 100.04 megahertz. Okay, so you need to continue this until the 7 sideband. Okay, you need to continue this until the 7 sideband. Okay, until the 7 sideband. Okay, so I will skip until J7. Okay, I will skip until, sorry. So J7 is equal to 0.02. Okay, so you can do the rest from J3 until J6. So P7 is equal to So I can give the value. So wait, I can give the value. I will give the value later. So P7 is equal to J7 square PC. So this is equal to 0 0.025 0 0.002. Okay. And here is FC 7FM. FC plus 7 FM. So this is 100 mega plus 7 times 10 kilo, 0 0.01. 100.07 megahertz. Okay, so you see that we have 7 pairs of sideband. So using the table, you get the power values and also the frequencies value. From here, you can draw the spectrum. Okay, you can draw the spectrum. So how to do the spectrum? So the spectrum is very long. Huh? So it is okay. So we have the center would be at 0.8 watt. This is 0.8 watt. So for example, here is 0.8. So this is power versus F in megahertz. Okay, so the center would be 100. Okay, which is 0. 0.8. 0.8. So the value is taken from the table. Okay, 0.8 watt power in term of watt. Power in term of watt. And then we have the first sideband 100.01. Okay, 100.01. The value is quite small, which is you see that 0.02. Okay, so 0.02 is you can make it like this, small. This is 99.99. This so this is 0.0245. Okay, and then we have the second sideband is located at 100.02, which is the value is 0.648. Okay, so 0.648 is somewhere here. Okay, 0.648. This is 99.98, 99.98. In the final exam, there'll be questions similar to this. So when you draw, don't use ruler because it's gonna waste a lot of time. Okay, so you just need to know to estimate, just to do the estimation of the height, 0.06, so 0.648. Okay, then we have here 100.02, here is 100.03, we have 100.04, 100.005, 100.06, 100.07. Okay, 100.07. So here we have 99.97, 99.96, 99.95, here 99.94, here 99.93. Okay, so if you see 100.03, the value is 0.9245, so it is slightly higher, this one. So I give you the value for the third sideband. Is it already calculate? Okay, it's not calculate in the table. So the value is 0.9 9245. Okay, 0.9245. So if you calculate on your own, if you continue the table, you will get this value. Okay, 0.9245 watt for the third sideband, and then for the fourth sideband you will get 0.392. Okay, so 0.392 is somewhere over here, and see that I just do the estimation in terms of height. So 0.392 watt, 0.392 watt. Okay, for the fifth sideband, okay, for the fifth sideband it is 0.08, 0.0845 watt, 45 watt. Okay, this is for the fifth sideband is somewhere over here, 0.0845, 0845. And then for the sixth sideband, it is located at 0.01. So 0.0125 watt. This is the sixth sideband is located at 0.0125 watt. And for the seventh sideband, the last sideband is 0.002, 0.002. This is 0.002 watt. Okay, 0.002 watt is located at 99.93 megahertz. Okay, so this is how you need to draw the power spectrum. Power spectrum means that power versus frequency. You need to draw correctly the spectrum. There are 7 pairs of sidebands. The center would be the carrier, and you need to label the frequencies and label the power values as well. If you draw like this, you will get full marks for that specific question. Okay, so class, if you have question, please ask me questions. Otherwise I assume that you understand this. So again, when you want,
Doktor,
yeah, yeah, please
nak
ask
tanya,
me.
kalau kat calculation kita ada salah,
Mm-hmm.
lepas tu kita buat dekat kita punya apa ni power spectrum ni
Mm-hmm.
ikut kita punya calculation. Macam mana doktor?
Okay, so you tanya kalau kira salah, and then you lukis menggunakan calculation you, macam tu ke?
Ya, maksudnya jawapan saya ambil daripada calculation saya dapat.
That means your marks will not be full marks.
Oh, dekat spektrum tu.
Yeah. So
Power spectrum.
normally like this, when we want to give the marks, we will see the first thing is whether you draw correctly or not. Okay, that's the first one. The second one is whether you label correctly or not. Okay, so if you draw correctly, that means you have 7 pairs of sideband and also the carrier component. That means your drawing is correct. But somehow there's maybe a few components that are wrong in terms of values. So if you ask me, you still get marks, but not the full marks for that question. Maknanya you akan dapat sebahagian daripada markah lah, dia bukan kosong lah. Is it okay?
Okay, Doktor.
Yeah. So maybe there might be some careless mistake, maybe during the calculations. So if you ask me, you will get almost full mark for that question. If you ask me, okay. I'm not very strict, so don't worry. I understand that if you maybe if you wrong some of the components, some of the values, maybe I can almost full mark, or maybe I can give you full marks for that one. No problem. Okay, as long as we can see that the drawing is correct, majority of the labeling is correct. Maybe one or two values is wrong. Maybe for me is no problem. I can give full marks for that one, so no problem. So don't worry about that. Okay. Ada lagi soalan? You have any more questions, other students? Is there any question? So in the final exam, you might have to have they ask about the carrier. So wait. Okay. In the final exam, so in the final exam, there's no drawing actually. Oh, okay. Oh, the final exam does not ask about this question, which is easy for you. So there's no drawing for the power spectrum. Oh, so it's more easier. Okay. So in final exam, you will not ask. There will not question. There will be no question about drawing like this, because this is gonna take some time. So there's no problem. Okay. So again, make sure before you draw the power spectrum, make sure you get all the values, then you can draw the spectrum. Okay. So if there's no question, let's move to the next example. Example 3.11. Okay. So example 3.11 is similar with this is similar with the previous example. Okay, very similar. So in FM transmitter, the frequency is changing between 100 to 99.98 megahertz, which with 4,000 times per second of fluctuations. So the amplitude of the FM signal is 5 volt. Okay, so the amplitude of the FM signal, so this is actually referring to the VC. Okay, and the frequency is 100 to 99.98. So that means if you draw the spectrum, that means it is fluctuates between two extreme points, which is 99.98. This is 100 100. So this is actually in terms of megahertz. So the fluctuations, you see that the fluctuations happens for about 4,000 times in 1 second. So the carrier change frequency from maximum to the minimum 4,000 times in 1 second. Okay, so this 4,000 times is actually referring to the frequency of the input message, which is FM. Okay, so the input frequency, the input message frequency determines the number of fluctuations per second. Okay, so the whole of this range of frequencies from minimum to maximum, so this is what we call as the carrier swing. Okay, and if you see that between maximum and minimum, the center would be the rest frequency, which is FC. So if we do if from this picture I can see that, oh, the center would be at 99.99. Okay, I can use saya boleh kira secara congak. So I can see that from this drawing I can estimate that the center would be at 99.99 megahertz. Okay, so now what? Uh, the first question asks you to find the carrier and the modulating signal frequency. Okay, so FC is equal to how much is FC? FC is equal to 99.98 plus 100 divide with 2. So in terms of megahertz, so we get 99.99 megahertz. Okay, so 199.98 divided with 2, so we get 99.99 megahertz. So this is for FC, while for modulating signal frequency FM is equal to the number of fluctuations per second, which is 4,000 times per second, or 4 kilohertz, or 4,000 hertz. Okay, and then what? Then the question asks, okay, then the question asks how much is the carrier swing. So carrier swing is the difference from the maximum to the minimum frequency, which is 100 mega minus 99.98 megahertz. Okay, so you will get this equal to 20 equal to 20 kilohertz. Okay, 20 kilohertz. And then what? Then the question asks you to draw the amplitude spectrum. Again, we need to do the the table again. Okay, so when we want to draw the table, we need to find the from the Bessel table. We need to see the Bessel table first. Okay, to get in order to find uh, the values of J, relative amplitude, so that we can draw the spectrum. Okay, so from here, uh, how we want to draw the amplitude spectrum? Uh, how to draw the amplitude spectrum? So what to do? So first of all, we need to find the beta, the value of beta. Okay, so how to find the value of beta? So beta is equal to beta f is equal to delta f over fm. Delta f is equal to carrier swing divided with 2. Okay, so remember that maybe I can put here delta F is equal to 20 kilohertz carrier swing divide with 2, so I get 10 kilohertz. Okay, 10 kilohertz of frequency deviation. Okay, so this is 10 kilohertz divide with 4 kilohertz. So this is about 2.5. Okay, so 2.5 in the Bessel table, you will get the number of significant sideband is equal to 5. Okay, the number of significant sideband will be equal to 5. So I need to add more slide. Wait there. Okay, so for n equal to n equal to 5, so that means uh, we can draw the table, another table. Okay, we can draw another table. Okay, so the first one is Jn, the relative amplitudes. Okay, the relative amplitudes. And this is about the amplitude spectrum. So amplitude spectrum, that means we want to find Vn in terms of volt. Okay, then we need to find the upper sideband frequency, sorry, lower sideband frequency, in this case in terms of megahertz. And then the upper sideband frequency, USB, in terms of megahertz. Okay, so the first one is J0. From the Bessel table, you will get negative 0.05. Okay, and from here you can get V0 is equal to J0 multiplied with Vc, which is negative 0.05 multiplied with 5. Okay, 5 is given in the table in the question. You see that Vc is equal to 5, so multiplied with 5 volts, so you get here is 2. Minus 2.5 minus 2, sorry, minus 0.25, sorry. So minus 0.25, and this is the center frequency, so there's no upper or lower because this is the center. Then we move to the the first sideband is J1 is equal to 0.5. Okay, so that means V1 is equal to 0.5 multiplied, sorry, J1 times Vc, so this is 0.5 multiplied with 5 equal to 2.5. Okay, and then for the sideband, this is lower sideband is Fc minus Fm, so this is located at 99.99 minus how much, 4 kilohertz. Wow, very small, 0.004. Okay, so this is 99.986986. This one is Fc plus Fm. This is 99.99 plus 0.004. So this is 100 point, sorry, not 100, 99 point. So this is 99.994, 994 megahertz. Okay, in term of megahertz. And J2 is equal to 0.45. So you get V2 equal to J2 multiplied with VC. So you get 0.45 multiplied with 5. So you get here is 2.25. Okay, 2.25 volt. And for the frequency, the lower frequency is located at Fc minus 2 Fm. The upper frequency is located at Fc plus 2 Fm. Okay, Fc plus 2 Fm. So Fc plus 2 Fm. And this is 99.99 minus 2 times 0.004. So this is 99.982 megahertz. And this one is 99.99 plus 2 times 0.004. So this is located at 99.998 megahertz. And you can do the rest. Okay, you can do the rest until J5. J5 is equal to J5 is equal to 0.02. J5 0.02. Okay, so therefore V5 is equal to 0.2 times V. Wait. So J5 multiplied with VC, so this is equal to 0.02 multiplied with 5. So you will get 0.1 volt. Okay, and for the lower sideband, this is Fc minus 5 Fm. For the upper sideband, this is Fc plus 5 Fm. And for the frequency, you see that here this is 99.99 minus 5, 0.004. So you will get this is a 99.97970 megahertz, while this one for the upper sideband 99.99 plus 5 times 0.004. So this is located at 100.010 megahertz. Okay, and this is not finished yet, so you need to draw the amplitude spectrum. That means you need to draw amplitude versus frequency. Okay, amplitude versus frequency. So this is V versus F in megahertz. Okay, so the center would be at 99. So 99.99. Okay, so 99.99. Wait, let me let me put the frequency, all the frequencies. So this is the first sideband is 99.994. The lower sideband is located as 99.986. 99.986. The second sideband would be at 99.998. Sorry, in 994. 994,998. So this is 99.998. And here is how much? 998. This is 100.002, 100.006, and 100.01. Whereas for the lower sideband, this is a 986, 982. So this is 99.982. This is 99.978. 978, 99. This is a 99.974. This is a 99.970. Okay. So when you want to draw the spectrum, maybe I can change the color. So here the spectrum, the center would be, you see that the center is minus negative 0.25. Okay, negative 0.25. And then the first sideband is 2.5. Okay, so 2.5 you can estimate, for example, at this height 2.5. So 2.5 volt. The second sideband is 2.25. So 2.25, I estimate the height would be somewhere here. So 2.25 volt, 2.25 volt. And then the third sideband is 1.1 volt. So 1.1 volt somewhere here. And the third sideband is 1.1 volt. 1.1 volt. The fourth sideband is 0.35 volt. So it is somewhere here, 0.35 volt. So 0.35 volt. And the last sideband would be 0.1 volt. 0.1 volt. Finish. So this is how you should draw the amplitude spectrum. Okay, this is how you should draw the amplitude spectrum. And then what? Next, the question asks you to find the power. Okay, so we have done this amplitude spectrum. So the question asks you to find the bandwidth by using Bessel table and by using the Carson's rule. So how to do this? So bandwidth by Bessel is equal to 2 times n times Fm. So this is actually equal to 2 times 5. Remember, we have 5 significant sideband multiplied with the modulating signal, which is 4 kilohertz. Okay, so this is equal to 40 kilohertz. So very easy. And then what we have, bandwidth by Carson. So bandwidth by Carson is equal to 2 times delta F plus Fm. Okay, so this is equal to 2 times delta F is equal to 10 kilo. So 10 kilohertz plus 4 kilohertz for the modulating signal frequency. So 14 times 2, we get 28 kilohertz. Okay, so this is bandwidth by Carson. Bandwidth by Carson, we don't need to use the Bessel table. Okay, and then what? Average power at the transmitter if the modulator carrier power is 5 watt. Modulator carrier power is 5 watt. Find the average power at the transmitter. Average power at the transmitter. Average power at the transmitter. If the modulator carrier power is 5 watt. Modulator carrier power is 5 watt. So the question asks you to find the average power at the transmitter if the modulator carrier power is 5 watt. So the total power is actually equal to power of the modulator plus power from the other parts within the transmitter. Okay, so maybe I can here. So P total. So remember that within the transmitter, within the transmitter, for example, here within the transmitter we have the modulator side. Okay, a part of the transmitter is the modulator. Okay, part of the transmitter is the modulator, and the rest would be the other components. Okay, and this produce the total power. Okay, this produce the total power. So this is actually the transmitter. Okay, so first of all, we can find how much is the total power. Then we can find how much is the remaining power. Okay, because the question give you the modulator power is equal to 5. Modulator power is equal to 5 watt. Okay, according to the question. And we don't know how much is total power. And we need to find how much is the remaining power, remaining average power within the transmitter. Okay, so first of all, find the total power, which is equal to VC square over 2R. Okay, VC square over 2R. This is the total power. So VC is given in the question. Okay, VC is given in the question 5 volt. Okay, so 5 volt. Okay, 5 volt square divided with 2 times R. R is given or not? Okay, R is not given in the question. R is not given in the question, so assume that R equal to 1. Okay, R is not given. Assuming that R is equal to 1, so 2 times 1, so we can get total power is equal to 12.5 watt. Okay, so this is the total power produced by the transmitter. Okay, the total power transmitted to the antenna. Okay, so now the question asks you find the P modulate the remaining power at the transmitter. Okay, P transmitter remaining. So this is the remaining. So this is actually equal to P total minus P of the modulator. Okay, so we want to find how much is the remaining total, how much is the remaining average power in the transmitter, excluding, okay, excluding the modulator. So that means this is 12.5 watt minus 5 watt. 5 watt is given in the question. Okay, 5 watt is given in the questions. So that means this is equal to 7.5 watt. Okay, 7.5 watt. Average power in the transmitter if the modulator carry power is 5 watt. Okay, so P total minus P modulator, so you will get 7.5 watt. Okay, any question?
Doktor,
Yeah,
yang N5 tu dekat mana?
N5. Which one?
N dia.
This one. N5. Okay. So I get N equal to 5. So N is the number of significant sideband. So how we want to calculate N? N is based on the Bessel table. So in order to find N, first of all, you need to find the beta. Okay, beta F, the modulation index, is equal to delta F, frequency deviation, divide with the modulating signal frequency. Okay, so how do I get the delta F? Delta F is actually carrier swing divide with 2. So 20k divide with 2, so I get 10 kilohertz. 10 kilohertz divide with 4 kilohertz, so I get 2.5. So 2.5 is for the modulation index. So from 2.5, I go to the Bessel table. Okay, let's see the Bessel table. So Bessel table, modulation index 2.5. So we will get the number of significant sideband is 5. So n equal to 5. Okay, so n equal to 5. So once we know n equal to 5, that means we can do the rest of the calculation. Wait, okay, so once I know n equal to 5, then I can calculate the Bessel bandwidth. Okay, and I can also do the rest of the parameters. Is it okay? Boleh faham tadi kenapa dapat n sama dengan 5?
Kau
Faham.
pegang ketiak aku.
Huh?
Faham doktor?
Okay, okay. Okay, any more question? Is there any question you want to ask? Ada soalan tak? If no question, let's move to the next topic. Okay. So there's no break because this is a recording session. You can take a break on your own. I will continue until 5 o'clock. Okay. And again, I will put this recording session in the YouTube so you can do the revision later. Okay. So if no question, let's. Yeah. Ada soalan? Tak ada Okay. So if no question, let's go to the next topic. Let's go to the next topic. Okay. Before we continue, can I get your response? Are you still there? Can you hear my voice?
Yes, doctor.
Yes, doctor.
Okay, thank you for the response. Okay, this is about pre-emphasis and de-emphasis. Emphasis, emphasize. Emphasize means that we increased. Okay, if we do de-emphasis, that means we decrease. So what are the things that we increase and decrease? So in this topic, we are actually discussing on how to increase the amplitude of the signal in order to get higher SNR. Okay. Now the issue that we want to see is about the SNR. Okay, signal to noise ratio. So the signal to noise ratio in angle modulated signal is uh, uh, is not high, especially when we use a higher higher modulating signal frequency. So that means if we use a higher FM value, there might be possibility that the SNR value that we achieve is lower compared to if we use a lower modulating signal. Okay, so the issue in FM is that when you use a higher modulating signal, there's a tendency that we might achieve lower SNR, and compared to the if we use a lower modulating frequency. Okay, so this is the issue. Now the issue is we want to increase the SNR. Okay, remember that theoretically we need SNR to be as high as possible. The higher the SNR would be better. Okay, so how do you want to increase that? Because theoretically, the higher the modulating signal frequency, the lower would be the SNR. Okay, so we need to do something so that we can achieve a better SNR at the output. Okay, so if you see from here, from this the left picture, you see that this is the uh, okay, picture on the left, center would be at FC. Okay, center at FC, and you see that in in the notes, in the lecture notes, that the output FM signal is a uniform signal because we use a uniform carrier signal. Why is it uniform? Because it is based on this picture actually. Wait, I will go back to the previous slides. Wait, So the amplitude is uniform. Okay, the amplitude is uniform in this lecture notes. Okay, so we use a uniform carrier signal to produce a uniform output amplitudes. That means the amplitude is actually not changing. It is actually based on the carrier amplitudes. Okay, so you see that if I go back to the slides, okay, if I go back to the slide, um, if the modulating signal frequency is higher, that means the number of noise level will be increased. Okay, this is a FM values, also FM values. So if you use a higher FM values, that means we will produce higher noise level. Okay, higher noise level for the higher modulating signal frequency. So what happened? If the noise level is higher, that means the ratio of signal level over the noise level would be small. Okay, compared to the SNR at lower modulating signal frequency, which is higher. So this is produce what they call SNR is not uniform throughout the values of modulating frequencies. Okay, so you see that the higher the modulating signal frequency, it will produce a higher noise level. And when we calculate the SNR signal level, okay, signal level is here, divide with the noise level, so you're going to produce a lower SNR, especially for the higher value of modulating signal frequency. So there's a non-uniform SNR for the different values of modulating frequency. So we need to improve this so that we can achieve better SNR at higher value of modulating frequency. Okay, so how to do that? In order to increase the SNR value, especially at higher modulating signal frequency, what we can do is we can do the process of pre-emphasis and de-emphasis. Okay, so pre-emphasis means that we will increase the the input the modulating we will increase the amplitude of the modulating signal before the modulation process at the transmitter, and then at the receiver side we will do the de-emphasis process to do the reverse process. That means when we increase at the transmitter, we need to decrease the same amount at the receiver so that it is balanced. When you increase the amplitude of the message signal at the transmitter, you might need to decrease the values at the same rate at the receiver again so that it is balanced. Okay, dia mesti seimbang. Kalau kita naikkan dia punya amplitude pada transmitter, that means we need to decrease the amplitude at the same amount at the receiver side. Okay, so you see that at this picture on the right. Okay, so when we increase the amplitude of the signal, especially for the higher value of modulating signal, okay, for the higher value of modulating signal, we increase the amplitude. So we might get output signal which with the SNR more uniform compared to without the pre-emphasis and de-emphasis. So you see that here, this is the SNR for the lower modulating signal frequency, and this is the SNR for the higher value of modulating signal frequency. So now we're going to see that the SNR is more uniform, okay, much better if we use a pre-emphasis and de-emphasis compared to the picture on the left. Okay, so here now we achieve a better SNR. So the word better SNR means that the SNR is higher. Okay, so this can be seen from the example in the Wayne Thomas's book. So I take this from Wayne Thomas's book. You see that this is at chapter 7, Wayne Thomas's 5th edition. So given a direct FM modulator VCO with a deviation sensitivity 1 kilohertz per volt. Okay, so this is at the transmitter side we have a VCO, and at the receiver side we have the PLL, phase lock loop demodulator. So VCO has a sensitivity parameter 1 kilohertz per volt, while the PLL has a sensitivity parameter 1 volt per kilohertz. Okay, so you see that the sensitivity parameters is different, volt per hertz and also hertz per volt. Okay, and in this example you are given 3 input signal. That means you are given 3 input message signal. Okay, 3 input message signal with different frequencies and amplitudes. The first one is 1 kilohertz at 4 volt, another one 2 kilohertz 2 volt, and 3 kilohertz at 1 volt. Okay, so the first question asks you to determine the frequency deviation at the output of VCO. So you need to find the delta F. Okay, and the second question is find the SNR. Okay, find the SNR given the noise level. Okay, given the noise level is given for each of the input, okay, which is 1 kilohertz at 0.1 volt. At 2 kilohertz the noise level is 2.5. At 3 kilohertz the noise level is 0.5. So this is the noise, given the noise. which correspond to each of the input. Okay, so you will see later that the question number 1 and question number 2 is about a system without using the pre-emphasis and de-emphasis. Okay, and then question number 3 asks you to repeat the first and second questions by using the pre-emphasis and de-emphasis. So how does it looks like? So you see that, so the picture on the left is for question number 1 and question number 2. Okay, so you are given 3 input signal at 1, 2, and 3 kilohertz with 4, 2, and 1 volt of amplitude. So this is the input is put inside the VCO at the transmitter. Okay, and the output of the VCO, we can find the delta F. Okay, the frequency deviation. Okay, that means the value of deviation. How much is the frequency? How much is the deviation from the rest frequency? Okay, so you see that the VCO produce 3 different delta F. So delta F can be found by multiply the amplitude and also the K1, the sensitivity parameter of the VCO. Okay, so I have here is a V1, V1, V2, and V3 multiplied with K1. So I get the output here, delta F1 is 4 kilohertz, delta F2 is 2 kilohertz, and here is 1 kilohertz for delta F3. Okay, so these are the delta F. So I get delta F1, delta F2, delta F3. Okay, so this transmit to the receiver. So the receiver has a phase locked loop PLL demodulator with another parameter, sensitivity parameter 1 volt per kilohertz. So from here, I can calculate the V out. So V out is calculated by multiplying the delta F, okay, multiply the delta F with the PLL sensitivity parameter. Okay, so delta F1 multiplied with 1 volt per kilohertz, we get 4 volt. 2 kilohertz multiplied with 1 volt per kilohertz, so we get 2 volt, and the other one is 1 volt. So this is the signal level. Okay, the signal level, and if we draw the spectrum, we will get like this, which is similar with the input. Okay, which is similar with the input. So this is the signal level. And if you see question number 2, you are given the noise level. Okay, the noise level is given at each frequency. So at 1 kilohertz, the noise level is 0.1 volt. At 2 kilohertz, the noise level is 0.25. And at 3 kilohertz, the noise level is 0.5. So from here, we can calculate the SNR for question number 2. SNR is given as signal level. Okay, so this is actually the noise level. So SNR is S over N, signal level, divide with the noise level. So for example, the first one at 1 kilohertz, 4 volt divide with 0.1 volt, so you get 40. SNR equal to 40. And then at 2 kilohertz, 2 volt divide with 0.25, so you get 8. SNR equal to 8. And then 1 volt divide with 0.5, so you get 2 at 3 kilohertz. So these are the SNR values at 3 different frequencies. Okay, at 1 kilohertz, the SNR is 40, 2 kilohertz, SNR is 8, 3 kilohertz, SNR is 2. Okay, so you see that these are the scenario that happens without the pre-emphasis and de-emphasis. Okay, tanpa ada pre-emphasis and de-emphasis. So if you see the picture on the right for the third question, question number 3. So question number 3 said that we put the pre-emphasis network at the transmitter before the VCO, and we put the de-emphasis network after the PLL at the receiver. Okay, so the pre-emphasis will increase the amplitude of the input. Okay, for example, here the input is 4, 2, and 1. So after the pre-emphasis, it will increase the amplitude to become this one. Okay, so this is just example. So the multiplication is 1. So this is 4 times 1. This is 2 times 2. The factor is 1, 2, and 4. Okay, because this is times 1, times 2, times 4. Okay, so at higher frequency, the factor will be higher. Okay, and it puts inside the VCO, and the output of VCO, we're going to produce a delta F. Okay, how much is delta F? Delta F is equal to 4 volt. Delta F1 is equal to 4 volt multiplied with the sensitivity parameter 1 kilohertz per volt. So we get 4 kilohertz. Delta F2 also 4 kilohertz. Delta F3 also 4 kilohertz. So this one we put inside the PLL, okay, with this transfer function 1 volt per kilohertz. So therefore we can produce the output voltage. Vout1 is equal to 4 volt. Delta F1 multiplied with KD, so we get 4 volt. Vout2 is delta F2 multiplied with KD, so we get 4 volt. This one, delta F3 multiplied with KD, so we get 4 volt. And from here, if we draw the frequency spectrum, it will look like this. 4 volt at 1 kilo, 4 volt 2 kilo, 4 volt at 3 kilo. Okay, and at the PLL, there's a noise, the same noise introduced in the PLL. So the noise would be at 0.1, 0.25, and 0.5. Okay, at 3 different frequencies. If you calculate, so this is S, this is N. If you calculate the SNR, okay, SNR, S over N, so we get SNR 40 at 1 kilohertz. Okay, 4 divided with 0.1. 4 divided with 0.1, we get 40. 4 divided with 0.25, we get 16. 4 divided with 0.5, we get 8 at 3 kilohertz. Okay, SNR is S over N. And after this, we need to reduce the amplitudes with the same amount. It is not finished yet because in the transmitter we have increased with a certain factor. Now we need to decrease the value with the same factor for both signal and also the noise level as well. Okay, so therefore, remember that here is, that means we need to divide with 1. Okay, this is divide with 2, divide with 4. So that means 4 divide with 1, we get 4. 4 divide with 2, we get 2. 4 divide with 4, we get 1. Okay, similar with the noise level. Okay, we reduce with the same factor, so we get 0.1, 0.125, 0.125. Okay, so since we reduce the same amount for the signal and also the noise level, that means we also produce the same SNR, okay, which is 40, SNR equal to 40 at 1 kilo, SNR equal to 16 at 2 kilo, SNR equal to 8 at 3 kilo. Okay, so the SNR is the same before de-emphasis and after de-emphasis, because we reduce the signal level and also the noise level as well. Okay, so the key point here is that we want to compare the SNR in question number 3 and also question number 2. Okay, you see that here previously we get 40, 8, and 2. SNR equal to 40, SNR equal to 8, SNR equal to 2. And now we get the SNR to become 40, 16, and 8, which is much better compared to the SNR value without pre-emphasis and de-emphasis. Okay, so the key point here is that pre-emphasis and de-emphasis will increase the SNR. Okay, because we want to achieve higher SNR as possible. Okay, so this is um, the FM signal generation. I mean the circuit, modulator circuit. Okay, so FM signal generation can be divided into two categories, which is direct FM, and the other one is indirect FM. Okay, direct FM means that we directly do the process of frequency modulation. Okay, direct FM means that we directly produce FM signal. Okay, so in order to do this, we can use a varactor diode, which is in this example. Okay, so in this example, we have this input modulating signal from here. The modulating signal is put inside to the base of the transistor Q1, and here VCC is over here. So remember that transistor act like a switch and also like an amplifier. Okay, if the voltage at the base more than the threshold voltage, that means the current can flow from collector to the emitter side. Okay, so you see that this is just example, one of the examples. So if you see in the real world scenario, there are many types of direct FM. One of it is what we call as a varactor diode. Okay, so you see that here the external modulating signal voltage adds to and subtract from DC bias developed by the R1 and R2. Okay, which change the capacitance diode at VD1 and the frequency oscillation by the oscillator. Okay, so positive alteration of the modulating signal increase the reverse bias at VD1 and increase the frequency of the oscillation. And then negative alteration of the modulating signal will decrease the oscillation frequency. That means for the positive alteration, positive cycle of the modulating signal will produce the output signal with increased frequency. Okay, so changes in amplitude of the input will produce a higher frequency at the output for the positive cycle, and for the negative cycle of the input signal will produce a small frequency at the output. Okay, so that means amplitude variation produce frequency variation at the output. Okay, so amplitude variation at the input produce frequency variation at the output. Okay, and then what? We have another one, what we call as the indirect FM. Okay, indirect FM means that we produce phase modulation first, which means that we are indirectly do the process of FM. Okay, indirect FM means that we are indirectly do the process of FM. How to do that? That means we do the phase modulation first. Okay, we do the phase modulation means that we are indirectly do the FM. Okay, so you will see later that in the indirect FM, we will produce narrowband FM. Okay, we do the phase modulation process, which indirectly do the process of FM. Okay, as I mentioned earlier in the class, that FM and PM are related to each other. Okay, if you change the frequency, you are indirectly change the phase. If you change the phase of the carrier, you are indirectly change the frequency of the carrier as well. Okay, So how to do this? Indirect FM. So indirect FM, you see that indirect FM, um, so indirect FM means that we will do the process of PM. Okay, so the information will be integral, will be integrated and then used to phase modulate the crystal control oscillator, which provide the frequency stability. So what does it mean by integral? Means that theta t, so theta t would be the integral of theta prime t dt. Okay, so this produce the narrowband FM. Okay, when we do this, that means we will produce narrowband FM. So if we want to make it as a wideband FM, we need to multiply it with a frequency multiplier. Okay, we can multiply the frequency to make it as a wideband later. Okay, so this is the block diagram. So this is the block diagram for the indirect FM. Okay, so we have here, you see that here we have the integrator. Integrator is this one. Okay, integrator. And then we have a narrowband phase modulator, which is this one, narrowband phase modulator. And we have the crystal control oscillator, which produced from the carrier. Okay, so this whole picture is actually referring to this part. Okay, so up to here, okay, up to this part, we produce a narrowband NBFM. Okay, so we are actually do the process of PM, but we are indirectly do the process of FM, which we produce a narrowband FM. And if you want to make a wideband FM, we need to use a frequency multiplier to increase the frequency of the output. So for your information, we have asked this question previously in the previous final exam. Okay, we have asked this question previously. So we use the same picture here, okay, where we ask the student uh, to identify or to produce the equations at for example at point A and also at point B, for example. Okay, we have asked this kind of question previously. Okay, so what you need to do is for example, here is a carrier. See that this is the carrier. So carrier, for example, carrier VCT is given as VC cos 2 pi FCT. Okay, and here is the modulating signal, the input message signal, which is given as 2 pi KF. MT is a VMT, so that means this is 2 pi KF VM cos 2 pi FCT. Sorry, FMT. FMT. Okay. And you see that the input carrier is put inside the 90-degree phase shifter. So what happened is that here would become VC sine 2 pi FCT. Okay. So 90-degree phase shift, 90-degree phase shift of cosine will produce sine. Okay, will produce sine. So you see that here is the integral process of the input message. So that means you will get integral of cos, you will get positive sine. Okay, that means at this point you will get 2 pi kf sine 2 pi fmt, and this is divide with 2 pi fm. Okay, so you see that 2 pi and 2 pi can be so this is kf vm vm. Okay, kf vm. So kf Vm over Fm. Yeah, I erase this one with So kf Vm sine 2 pi Fmt. Okay, you divide with 2 pi f. So 2 pi and 2 pi can be cancel out. So here we have a kf Vm over Fm. So you see that here kf Vm over Fm. So that means this is actually equal to beta f sine 2 pi Fmt. Okay. And then what? And then we put inside the phase narrowband phase modulator. So you see that the symbol X here means that it will do the process of multiplication. Okay, that means carrier multiplied with the input message signal, sign multiplied with sign. So that means at point A, okay, at point A, okay, at point A, we will get this one, the output of the narrowband phase modulator is equal to Vc beta f, okay, sine 2 pi fct sine 2 pi fmt. Okay, and you see that sine and sine, so you can get here is according to the trigonometry identity, so we can rearrange the equation to become like this, Vc beta f over 2. Okay, so sine and sine is cos 2 pi fc minus fm t minus cos 2 pi for the upper sideband fc plus fm t, close bracket. Okay, so this is at point A. What happened here, you see that here is here at this point you will add with the input, which is Vc cos 2 pi fct. So both of these input plus output at point A. So we get here is the narrowband. Remember narrowband, we will produce a signal similar with the AM. Okay, if you remember, narrowband FM is similar with double sideband full carrier. Okay, so therefore at point B, okay, so I put here at point B, okay, it is equal to Vc cos 2 pi fct, okay, plus Vc beta f over 2 cos 2 pi fc minus fm t minus cos 2 pi for the upper sideband fc plus fm t, close big bracket. So you see that we have three components. If you draw the spectrum, okay, if you draw the spectrum of V versus F, okay, you have the carrier over here, you have the upper sideband, and you have the lower sideband. So the carrier is Vc amplitude, the amplitude is Vc. The amplitude for the sideband is Vc beta F over 2. And here is Vc beta F over 2. Okay, frequency is Fc, Sc plus Fm, Fc minus Fm. Okay, and if you want to calculate the bandwidth, again the bandwidth is equal to 2 Fm. The distance is Fm and Fm, 2 Fm. Okay, and if you want to calculate the power, you see that we can do many things. Okay, the total power is equal to PC plus PLSB plus PUSB. Okay. So this is the narrowband FM. And you will see later, if you want to increase the frequency, because we produce a narrow band. Now, if you want to use it as a wideband application, we need to increase the frequency by using the frequency multiplier. Or there's another method, what we call as the heterodyning methods. So you're going to see later for the up conversions. Up conversions means that we increase the frequency. We increase the frequency of the signal to become wideband, from narrowband to become wideband. Okay. So these are the questions that we have asked in the previous final exam. Okay, pernah ditanya. Okay, we have asked this previously, which you need to produce this equation, this kind of equations. Okay. Okay, so now is 4:56. I thought that I can finish chapter 3, but I cannot finish chapter 3. So maybe I need another week, and then we can continue with chapter 4. And I think maybe I need to do extra classes to replace the holidays. To replace the holidays. So okay, so now let's take the attendance. Okay, let's take the attendance. Before that, can I get your response? Are you still there?
Yes, Doctor.
Okay.
Ya, doktor.
Sekejap, So, so you can open your QR code reader. So after taking your attendance, you can go out. Okay. So I will open the attendance for today is section 1. Section 1 is this one. Okay, so you can take the attendance. Okay. So see you again next week.
Thank you, Doctor.
Okay,
Thank you,
welcome.
Doctor.
Okay, welcome.
Thank you, Doctor.
Okay, welcome.
Thank you, doktor.
Okay, welcome.
Thank you, Doctor.
Okay, welcome.
Thank you, doktor.
Okay, welcome. So if you already take your attendance, you can leave the class. Okay.
Doktor,
Yeah.
saya tak boleh scan.
Okay. Nama siapa?
Nur Fakira.
Ni Nur Fakira.
Ada, Doktor?
Okay.
Ya, saya.
Nombor 39.
39 Nur Amirul. Okay,
Ah,
dah.
Ustaz.
Siapa lagi? Any more? Siapa? Nur Niwina siapa? Nur Niwina? Dah ambil attendance belum? Nur Niwina. Okay, Nur Niwina. Okay, I already take your attendance.
Doktor, Nur Hidayat, doktor.
Okay, okay. Settle. Fadilah ada? Fadilah. Nur Fadila ada kan? Fakira ada. Fadila tak datang Okay, so one student absent today.
Doktor,
Ya? Ya, tak dengar.
Fadilah Imanina tadi ada.
Oh, dia ada tadi
Fadilah Imanina tadi ada.
Dia ada tadi So saya anggap dia datang lah Okay, so that's all.
Doktor, saya nak tanya pasal projek.
Okay. Okay, silakan.
Maksudnya kena buat dalam software satu, hardware satu ke?
Macam mana hardware satu? Tak faham. What do you mean?
Projek tu kena buat dalam hardware juga ke?
Oh ya, kena buat hardware lah. Ada hardware.
Yang
That means you kena ada transmitter dengan receiver. So kita punya objektif adalah kita nak hantar signal daripada transmitter kepada receiver. You kena buat hardware dan kena buat hardware lah. So yang software tu sebenarnya is more on the just for simulation before you pasang dia punya hardware tu. You akan buat simple simulation just to see the output je lah. But the output yang real punya adalah dia punya hardware tu lah sebenarnya. Okay.
simulation tu maksudnya buat yang dalam Proteus tu ke?
Ya, Proteus. Proteus tu mungkin ada sebahagian yang komponen tak ada dalam yang hardware tu. You boleh gantikan dengan komponen lain lah. Yang mana kita boleh agak-agak dia punya simulated output tu lebih kurang sama lah. But the thing is kita nak produce yang hardware tu sebenarnya. Yang simulation tu untuk membantu kamu untuk membuat hardware design tu sebenarnya. Dan kita sebenarnya benarkan menggunakan Arduino, which is lebih mudah sebenarnya kalau kita nak buat transmitter receiver tu. So ada sedikit lah programming sedikit.
Faham.
Boleh?
Yang untuk receiver tu doktor, maksudnya macam mana nak cakap? Kiranya dia receive signal tu dekat komponen tu lah ke benda tu dari phone ke speaker ke macam mana?
Okay, sekejap So sebenarnya kita akan macam mana nak cakap sekejap. Mungkin saya lukis sikit Sekejap. Mungkin kat sini saya lukis sikit sekejap. So apa yang kamu buat adalah kamu akan ada transmitter dan kamu akan ada receiver lah. Okay, receiver. So yang di sini input kepada transmitter ini biasanya kita akan sambung kepada kita punya mobile phone So mobile phone ni kita akan play music kita akan play music. So dia akan hantar masuk ke dalam transmitter. Transmitter akan hantar menggunakan FM signal lah. FM signal and then pada receiver dia akan absorb the signal and then dia akan produce the same output lah. Ini yang kita akan sambung kepada speaker nanti So apa yang you transmit lagu tadi, contoh music kita akan dengar dekat speaker nanti. Okay.
Itu komponen lah ke dari phone?
Macam mana?
Phone tu input.
Input dia. Input
Speaker dia speaker kecil tu lah.
Speaker kecil?
Ke guna LED?
Oh, you nak guna input dia speaker? Speaker maknanya you kena
Maksud saya yang output tu.
Okay, yang output ni. Speaker maknanya as long as kita boleh dengar you punya input tu lah. So you boleh letak a simple speaker. Just kita nak dengar lagu tadi lah. So kalau signal itu berjaya dihantar, that's it. Itu aja. Sebenarnya kita nak lihat signal ini dihantar daripada transmitter sampai receiver dan kita boleh dengar semula. Okay. Komponen dari segi komponen you boleh
Doktor, kalau selain
ya. Macam mana?
Lain guna dari speaker boleh ke? Sebab macam speaker susah. Kalau
Contohnya,
dekat sini susah nak cari speaker.
selain speaker, apa cadangannya? Kalau ada
Kalau guna
tak dengar.
LED,
LED lampu.
LED.
Oh, LED lampu.
Bukan. LED signal apa tu? Macam screen.
Okay, as long as kita boleh dengar, kita boleh dengar audio tak? Kita boleh dengar audio tak output dia?
Oh tak, maksudnya keluar signal saja.
Tak, kita nak dengar voice
Tak
tu
boleh
kan. Kita dengar suara tu.
Oh,
Sebab tadi you
faham.
hantar input contoh suara ataupun music daripada satu device. Contohnya mobile phone lah contoh. Mobile phone ni biasa dia akan sambung guna audio jack masuk ke dalam transmitter. Transmitter ni proses dan dia akan hantar signal tu sampai kepada receiver, and then kita akan proses, and then dia akan keluar outputnya lah. Kita akan dengar music yang sama lah macam tu. Okay.
Okay, betul.
Boleh Is it okay?
Okay, doktor. Thank you,
Dari
doktor.
segi komponen, you boleh ambil komponen daripada E-komponen. Boleh
E-komponen.
FKE ada E-komponen. Kalau you perasan, you boleh mohon komponen daripada fakulti, dan bakinya you boleh dapatkan daripada kedai kat luar lah. Okay.
Kami dah ada mohon dah.
Oh, dah ada Okay, that's good lah. Boleh
Okay. Thank you, doktor.
Okay, welcome.